Hi, welcome to this video where I will tell you about observables in gauge theories. Gauge theories include the standard model of particle physics and within it electromagnetism. And as theoretical physicists, we want to know what we can calculate in those theories, and those are observables. And if we were experimentalists, we want to know what we could measure, or we want to know what our experimentalist friends can measure. And this is why this topic is important. It is also important because we study gauge theories a lot, supersymmetric gauge theory or non-supersymmetric gauge theories in theoretical physics, and the only measurable quantities are gauge invariant objects. So let me explain what these are. To start, let me set the stage. So we are looking at gauge theories, and those include Maxwell electromagnetism in any dimension. Today I will focus mostly on 4 and a bit on 2. There is Chern-Simons theory in 3D or 5D, but I will not talk about this today. There is Young-Mills or QCD, and again it can be in 2 to 10D, but I will focus on 4. And then there are all kinds of generalizations, like quiver gauge theories, if you want the standard model. And gravity is also some sort of a gauge theory, and likewise higher spin theories, but I will not talk about those today. So what observables are there? So we have local operators, line operators, surface operators, you can also define scattering amplitudes, and there are some more. But I will focus mostly on line operators, but also talk about local operators and surface operators a bit. So let us start with gauge theories. So in a gauge theory, you will have a vector field, a mu, in the algebra, little g, of the gauge group, capital G. If we are talking about higher spin gauge theories, then they will not be vectors, they will be a higher representation of the Lorentz group, but I will not talk about that today. So we are only looking at vector fields. And in the examples we study today, G will be equal to U1 or to SUN. And sometimes it is important to distinguish between SUN and SUN mod Zn. And there are different observables in these theories, but I will not discuss that today. Under a gauge transformation, the gauge field will transform as follows. It will be conjugated by a matrix U in the group, and there will be this term with a derivative. I'm sure you're very familiar with that. Charged field will transform according to the representation therein. a fundamental field transforms like this, and an anti-fundamental like this, and an adjoint gets conjugated, which is the action in the adjoint, and there can be many other fields and other representations. I will not write them here. Observables need to be gauge invariant, meaning they should be singlets of the gauge group G, and they should transform to themselves under gauge transformations. So in the rest of the video, I will tell you about the following. I will start with Maxwell theory, mostly in 4D, but also a bit in 2D. I will discuss to what extent the flux is a gauge invariant object, and I will define Wilson loops. I will study in detail three classes of objects: the parallel lines, or a rectangle, if you want it to be closed, the circle, and the cusp at an arbitrary angle phi. I will then talk about Yang-Mills in 4 dimensions, which of course is a much more complicated theory, and I will define gauge invariant local operators. I will define the Wilson loop, which is much more complicated to define in 4D, and we'll discuss properties of these same Wilson lines as above. They cannot be calculated exactly anymore, but some of their properties are very characteristic and are important, so I will discuss those. There is one more interesting kind of Wilson loop observable, and that is a Wilson loop with insertion of local operators. I will then define 't-Hooft loops and surface operators, but I will not discuss them in great detail. So we start with Maxwell theory in 4 dimensions, and the Lagrangian is simply f squared, and here mu naught is the usual constant from electromagnetism. Later I will replace it with E, the charge of the electron. And we can write it in terms of the electric and magnetic fields. Both of them are inside F, as follows. In this case, the element of the group associated with gauge transformations, U, we can just write it as E of lambda, where lambda is an arbitrary function, and then this derivative term is just the derivative of lambda, and the gauge transformation of the gauge field is as you're used to in electromagnetism. The field strength, which includes the electric and magnetic fields, the derivative of the potential, and because of the antisymmetry, it is gauge invariant. It transforms to itself. So it on its own is a good gauge invariant observable. The simplest example is the charged particle. It's our first problem we always deal with in electromagnetism, where the potential is just Q divided by 4 pi r, and the electric field is just the derivative of that, and it's the vector r times Q divided by 4 pi r cubed. If we switch to spherical coordinates with the direction 0, r, theta, and phi, we get that f0r is just q over 4 pi r squared. And now Gauss's law is very simple. The integral of this f times the measure factor on a radius r sphere is just a charge q. If instead of an electric particle we assume we have a magnetic particle, the field strength would be the Hodge dual of what we had before, so it will have components theta and phi and be proportional to the volume sine theta with a proportionality constant m over 2. We can then integrate it to find the vector potential, and we chose the integration constant, this 1 here, such that this is regular at theta equals 0, and this is the good gauge for the north, around the north pole of the 2-sphere. But if we want to continue to the south pole, we will get a non-zero a phi at theta equals pi, which is singular, so we need to change a gauge. That singularity, of course, is the Dirac string. So I call this the north gauge field, and the south one will be equal to m over 2 minus 1 minus cosine theta. And the difference between them is simply m, which is the derivative of the function m phi. And then if I demand that u equals e to the I m phi is single valued, that will tell me that m is an integer. This, of course, is the Dirac quantization condition. Even simpler solutions of Maxwell are for the infinitely charged plane, in which case we have a constant electric field pointing out of it. Likewise, we can take an infinitely charged magnetic plane with a constant magnetic field pointing out of it. Both of those configurations have infinite area and infinite flux, and therefore also infinite energy, so they're not really physical. But they are very good observables when your space is compact. When you have a torus, it's very natural to put a constant magnetic field on it. Of course, in reality, we don't have magnetic charges, and to create a magnetic field, we use a solenoid or a magnet. But again, if we wanted to be in all of space, you would need an infinitely large solenoid, and that is unrealistic. And instead, you can, if you have a torus, you can just take the magnetic field and you don't even have to worry about the sources. It's just a solution to the Maxwell equations. Whatever magnetic field we have, we can define the flux through any domain sigma, and by Stokes' theorem we can write it as an integral over A. So let's examine again the case of the magnetic flux on the 2-sphere and take sigma to be this region above a latitude theta. So this is the flux, and this is indeed equal to the integral of the northern potential. But it is different from the integral over the potential if we took the other form of the potential, valid for the southern hemisphere. So the definition of the flux in terms of the magnetic field was well defined, but not in terms of the potential, because the potential is subject to gauge invariance. But if we take the exponential of it with an I, then the two expressions that we find are equal to each other, because the difference between them is the integer m times 2 pi I. So while A is subject to gauge transformations, is not single valued, if we define the exponent of e to the IA, that is single valued, and that is the abelian Wilson loop. We can view the Wilson loop as an extra source term to plug into the action and solve for the field configurations with the extra source given by the Wilson loop. So this is a good time for you to pause and try this exercise, which has two parts. The first part is in 4 dimensions to take a straight line along the Euclidean time direction and solve the equations of motion with the appropriate source written here. And the second part is to look at 2-dimensional Young-Mills, where the electromagnetic field has a single component. It's called F12 when I'm in the flat 1-2 plane. And I'm asking you to solve for F12 in all of space in the presence of an arbitrary non-self-intersecting Wilson loop. And you need to impose that f goes to 0 at infinity. But then you can solve for it in all of space, regardless of the shape of the loop. So now let me look at some particular examples of Wilson loops. And the first example are the parallel lines, where I assume that they go along a very long time t in the Euclidean time direction and separated a distance L. And you can connect them in the infinite future and the infinite past with lines of length L to get a closed curve. So the Wilson loop has 4 sections. You start at minus t over 2 and minus L, and you move along the x1 direction. Then you are at minus t over 2 and 0, and you move in the time direction, and then you close with the 2 other edges. To evaluate it, I will rely on the solution to exercise 1, so please do it now before I continue. To do that, I need to assume that t goes to infinity, because I had there the line, the infinite line. And I will split the Wilson loop into 3 pieces. And this piece will be the one that I will consider as my source. And then I evaluate the 3 other pieces in the background of this source. If you do the homework, you would find, of course, the usual Coulomb potential, and you can write the gauge potential as follows. And now you can see that because A1 is equal to 0, that these 2 terms will not contribute at all. And all you need to calculate is this term, E squared here is some strength of the electric field. It can be the charge carried by these Wilson loops, or you can leave it as the original epsilon naught and the standard definition of Maxwell equations. So we find that the Wilson loop is the exponent of t over L, where t is the infinite time and L is the finite distance between the two lines. We will get back to this later. As the second example, I take the circle of radius r in the x1, x2 plane. The Wilson loop is equal to the exponent of the integral of a mu along the curve multiplied by the tangent vector x dot. And this is what you get when you evaluate the derivatives of x1 and x2 with respect to tau. Now let me look what happens if I have two factors of this term inside the Wilson loop, and I take the expectation value of it. So in the numerator, we get the product of sine tau and psi tau prime and cosine tau and cosine tau prime. In the denominator, we get 4 pi squared times 2r sine tau minus tau prime over 2, all that squared, which is the chordal distance, which you can see if you take here tau and here tau prime, and you want to calculate this distance twice this half theta angle. And here we used that the propagator in coordinate space is as follows. So we can integrate over one of the angles and be left with only the relative angle that I will call sigma. Now we use the trigonometric identity to write cosine sigma as 1 minus 2 sine squared sigma over 2. So we can split this term into 1 over sine squared sigma over 2, and another term which is just the integral over sigma times 1 over 4 pi, which just gives 1/2. This integral is just minus 2 cotangent of sigma over 2 evaluated between 0 and pi, where in both ends it diverges linearly and we can safely ignore it. So the answer is 1/2, but if I kept the electric charge E in this calculation, I would get E squared over 2. So now I want to calculate things to all orders, and then I will expand my Wilson loops in powers of the gauge field and take Wick contractions, but I need to include only even number of fields, so I need to look only at the even terms in the expansion. So we have 2n copies of this integral, and we take the expectation value of all of this. But now we do a Wick contraction, and so the first a can be contracted with 2n minus 1's, a's, and then we get rid of another one. And then the next one can be contracted with 2n minus 3 of them. And so we find this combinatorics with a double factorial. And now we have the free two-point function, and all that to the nth power. And now we can plug what we found before. and use that 2n factorial is equal to 2n double factorial times 2n minus 1 double factorial, which is just the exponent of e squared over 4. And this e squared again is the charge of the electron. It's not 2.17. It's now a good time to pause and do the second exercise, which again has two pieces. And the first one is to redo the calculation of the parallel lines, but now using propagators. And in this case, you can actually do it exactly even for finite t and finite L. So try that. The second part of the exercise is to redo the circle calculation, but now using semi-classics, just electrostatics. And as a hint, note that Maxwell theory is conformally invariant. The third example is very close to my heart, and that's the cusp. And here we parameterize the first ray coming from the left to the origin for tau less than 0. And then we have the second ray going from the origin at an angle phi. That will be for positive tau. Note that phi here is a constant. So I evaluate now the propagator between the two rays. Propagator between a ray and itself will not give anything interesting. And so we have the integral from minus infinity to 0 of a1, and then the integral from 0 to infinity of a1 cosine phi plus a2 sine phi. And the first integral is d tau, the second integral is d tau prime, and the only contraction we have is of a1, so this gives us minus e squared cosine phi over 4 pi squared, and then the integral and the distance. So we can write it as follows, and then in order to do the integrals, it is useful to replace tau and tau prime, which are integrated over a quadrant of the plane, rewrite them in terms of polar coordinates, where rho goes up to infinity and chi is between 0 and pi over 2. So we get this integral with the measure rho d rho, and then the integral d chi. And now I rewrite this distance in terms of rho and chi. And of course, it's obvious that I can take the powers of rho out, and I just get integral of rho d rho. And then I get this complicated angular integral, but luckily Mathematica knows how to do it. And now we need to evaluate this arctan between 0 and pi over 2. At pi over 2, tan chi diverges, so arctan gives us pi over 2. And then at chi equals 0, we get arctan of cotangent phi, which is pi over 2 minus phi. So this whole thing is just equal to phi. So we find this answer, and we had to put a UV and IR cutoff epsilon in L, and we get this log epsilon, and this is an indication of an anomaly which arises here in what is a semi-classical calculation. So we can attribute a dimension to this cusp operator. And the dimension is this prefactor, e squared cotangent phi times phi over 2 pi squared. So exercise 3 will be with the cusp, and the first part would be to exponentiate this calculation, which is very similar to the exponentiation of the parallel lines. The second part of the question is to evaluate this using semi-classics to get this result from electrostatics. So we finished an introduction to Maxwell theory and what Wilson loops are. We looked at 3 examples of Wilson loops in Maxwell theory. And now we're ready to turn to non-abelian gauge theory, to Young-Mills theory. So the Lagrangian is now 1 over 2 g squared, where g is the gauge coupling trace f squared, or we can write it as 1 over 4 g squared f mu nu a, f mu nu a, where a is an index in the algebra. TA are generators of the algebra, and they satisfy that trace TA to B is equal to 1/2 delta AB. Of course, the algebra relation is that the commutator of TA and TB is the structure constant times TC. The field strength is given as the derivative of a potential, where we can write it in this form with the commutator of A mu A nu, or if we write F mu nu A, we can use the structure constants F A B C, A mu B, A nu C. And of course, gauge theories have a gauge invariance where A mu transforms in the adjoint plus this derivative term, and U are space-dependent elements of the group G. In the non-abelian theory, the integral of A mu is no longer gauge invariant, and its exponent is also not gauge invariant. Also, the field strength is not gauge invariant. So if we have fundamental fields, like say a fermion psi, which has standard action, this Lagrangian itself is a gauge invariant object. So indeed, psi transformed to U times psi bar transformed to psi bar U dagger, and then psi bar psi is gauge invariant as it is if we insert more derivatives and field strength in it. With only the gauge field, the simplest gauge invariant operator is trace f squared, which is again the Lagrangian. Trace f is also gauge invariant, but it is 0 for SUN. So I told you that the integral of A is not gauge invariant, but we can still define Wilson loops in non-abelian gauge theories that are gauge invariant. And to see that, we define the following: an object along a path from the point x to the point x prime. So it is given in terms of the exponent of the integral of A from x to x prime, here parametrized in terms of y of t. But it's not really that, because of this p symbol, which is called path ordering. So if you think of a Riemann integral as a limit over a sum with small intervals, the path-ordered exponential of an integral is the product, a limit of a product over many small things, and path ordering keeps this product in a particular order for objects that do not commute. So the Wilson loop is the limit of n going to infinity when we divide this interval between 0 and 1 to n smaller intervals, and we take these products of 1 and parts of the gauge field. And note that y mu of 1 minus y mu at the nearby point is similar to the derivative y dot that I had in the definition above. And then the last term is when you have the interval between y mu of 1 over n and y mu of 0, which is very close to the point x. Note that the ordering here is from right to left. Smaller numbers are on the right. Larger numbers, when t is close to 1, is on the left. Now we claim that under gauge transformation, this open Wilson line from x to x prime transforms with a u of x prime on the left and a u dagger of x on the right. We can check this for the infinitesimal pieces, where I multiply from the left by y of t and from the right with y dagger of t minus 1 over n, and I insert the usual term from above in between, and I Taylor expand this term on the right around t. But this y dot I can again write as y of t minus y of t minus 1 over n, all that multiplied by n. And now if I insert it, ignoring terms of order 1 over n squared, where this is the gauge transformed A mu. There is another derivation which is more elegant, and here I differentiate with respect to the point x prime, and x prime is the upper limit of the integral, and it is the leftmost part of the Wilson loop, so it will bring down an I a mu at x prime times w. So it satisfies this covariant derivative equation, which is the same as the behavior that you would expect from an object that transforms in the fundamental. So that's why I transform with a u at x prime on the left. And likewise, when we differentiate with respect to x, we bring down an a mu of x on the right, so it satisfies the covariant derivative acting on the right as would be appropriate for gauge transformation with respect to u dagger on the right. This Wilson line from x to x prime is not gauge invariant, but if we go along a closed path from x to x, we can take the trace, and that will give us a gauge invariant operator. There are some generalizations. So if we have fundamental and anti-fundamental fields, we can put them at the two endpoints. So now we have an open Wilson line with a fundamental and anti-fundamental field, and this is gauge invariant. Or if we have adjoint fields, we can insert them along the Wilson line. So here we have one insertion at the beginning and end point, and you can check that it's gauge invariant, but we can actually include many of them. So this is gauge invariant, and phi can be a field, or it can be any other adjoint valued operator. We can write this elegantly in terms of the path ordering symbol, which will make sure that things are inserted in the correct place. This makes sense as long as the points x and x prime are along the curve C. It is now time for exercise number 4. So consider an arbitrary curve that you add to it a small square, as in the picture, where every side of the square is of length epsilon, and try to write it to order epsilon squared in terms of an operator inserted into the Wilson loop without this square. And the question is, what is this operator insertion x? So we defined what Wilson loops are, and we proved that they are gauge invariant. But what are they as observables? What can we calculate with them? So the first example is the same example we looked in Maxwell theory, that of the antiparallel lines. In electromagnetism, we saw that it was equal to the exponent of some number times t over L, where t is the length and L is the distance between the lines. And we can interpret this as arising from a potential V of L. And we see that in this case, this is a conformal Coulomb-like potential. Now this behavior that is extensive in T is expected to be valid for any theory, and it always will calculate the effective potential between the charged particles represented here by the Wilson loops. So we always will have a potential V of L. And there are three standard behaviors. There is the Coulomb behavior we found before. There is a behavior proportional to L, and then it would have to be divided by the square of some length scale, which is normally called alpha prime, the string scale squared. This arises in confining theories, of course. In that case, T times V is equal to the area encircled by the Wilson loop. The last case is when V does not depend on L, and then the theory is screening. The two lines essentially do not see each other. In general, gauge theories cannot be solved analytically, and it's a hard problem to determine it. And of course, if you can calculate that for Young-Mills it behaves like the area, you proved confinement, which has not been done yet. Another case that we can look at is the circle, as we did before in electromagnetism. Normally it's not done, but there really isn't a good reason not to do it. If you work on the lattice, it's easier to do a rectangle, but if you do things analytically, you might as well use a circle, and you can get the same amount of information out of it. If it does not depend on the radius, then it is conformal, as in Maxwell theory. If it behaves like an exponent of the radius squared divided by alpha prime, so again we have an area law, then that is the confining phase of the theory, or confining theory. And if it is proportional to R, and the proportionality constant would normally be a mass of a charged particle that is screening the lines, that would be a screening phase. The last example is a cusp, where in Maxwell theory we saw this anomaly, the logarithmic divergence. So this is the one loop anomalous dimension, and it really behaves like an anomalous dimension there in a conformal theory. If we take a Wilson loop with two corners with the same angle phi, and we calculated the anomalous dimension, which I will call delta, which is the coefficient of the log divergence, then what you will get is that the expectation value of the Wilson loop will behave like 1 over the distance to this power. Even though the theory is conformal, we find an explicit dependence on the distance in the same way that when we have operators of any dimension, their two-point functions will depend on the distance. So the cutoff introduced a length scale into the problem, and therefore we have the behavior which scales with the distance, but is not independent of the distance. Young-Mills theory in general is not conformal, but still these kinds of divergences will arise. And to treat them properly, what you need to do, whether you have insertions into the Wilson loop or corners, each of them will give rise to logarithmic divergences. And in the same way that you treat local operators, you need to add the z factors that will renormalize your operator, and it is not a completely trivial statement that they are multiplicative. And therefore you write this product of these z factors multiplying the Wilson loop, and then it can be renormalized properly with the dependence on the scale absorbed in these z factors. So this is the way you will get the Wilson loop above, and that will depend on the distance. And in a theory like n equals 4 super Yang-Mills, which is conformal, you can evaluate these z's, and you can evaluate these anomalous dimensions, and you can use integrability to calculate these anomalous dimensions as a function of the gauge coupling. In electromagnetism, we have explicit magnetic electric duality, and we can define a magnetic particle and a magnetic line, and I wrote it in the simplest case. In non-abelian gauge theories, it's more complicated because if the flux is not gauge invariant. Still, one can define an object, and it's called an Hooft loop, and there are two definitions for it. There is the traditional one given by Hooft, and there is a more modern one given by Kapustin. Hooft's definition relies on the notion of the Dirac string. In 3 dimensions, you know that you can link a line with a circle. In 4 dimensions, it's linked with a 2-sphere. Hooft wants us to calculate Wilson loops along this 2-sphere at latitudes. And what he wants us to see is that at the North Pole we have a trivial Wilson loop when we go around an infinitesimal circle. And then as we grow, it's no longer trivial. And then when we go back to the South Pole, we again have an infinitesimal Wilson loop. But now it should pass around the Dirac string. So the phase will not be 0, it will be an integer multiple of 2 pi. So this is the way Hooft defined it, and you should read his original paper to understand it better, but it's not particularly easy. Kapustin defines the Wilson loop in terms of an infinitesimal sphere close to the line, and he demands that the field configuration will approach that of a Dirac monopole up to a gauge transformation in the vicinity of the line. So he sets singular boundary condition along the curve. So we have arbitrary integers mi. They need to sum up to 0 because we're in SUN, not in UN. And they all are all integers. So this is Kapustin's definition. Now, if we follow the logic of how things should behave, and again, this was done by Hooft in the 70s, we would expect again to find that these Wilson loops, either the parallel lines or the circle, will have these kinds of behavior that we discussed, where they now calculate a magnetic potential. So we again find 3 behaviors where the magnetic particles exhibit conformal behavior, where the magnetic particles confine, and when the magnetic particles are screened. And following the logic of Hooft, the conformal behavior is the same in the electric and magnetic case. Both of them would be conformal. if magnetic charges are confined, then you have a free charged, electrically charged particles. So electrically charged Wilson loops will be screened. And vice versa, if you have magnetically charged particle that cause magnetic screening, then your electric theory will be confining. The last thing I wanted to talk about are surface operators. And let me just define a class of surface operators in the non-abelian theory. You can do the same thing in Maxwell theory. And I will define it in the same way that Kapustin defined the monopoles. Now, if we have a surface in R4, you can link it with circles. And now we want to ask what happens to the gauge field for infinitesimal circles around it. So we have these circles that go around the surface, and we should think of them as non-contractible. And so even though they get very, very small, it doesn't mean that the gauge field has to vanish around them, but instead you can have non-trivial Wilson lines as a background around this singular surface. And again, because we're in SUN, we need to require that they add up to 0. And now these alphas have to be between 0 and 1. It is easy to show that if they are greater than 1, then you can apply a regular gauge transformation and shift it by an integer. So in the case of the flat plane in the x3, x4 direction, I can take polar coordinates in the x1, x2 plane, r and phi, and then simply demand that A near the origin behaves like this. It's proportional to d phi. This is only the behavior for infinitesimal r. So finally I have the last exercise, which is harder, and that is to define local operator insertions into an Hooft loop or a surface operator in such a way that they are gauge invariant. So this is where my talk ends. I started with a long discussion of Maxwell theory. I wanted to introduce Wilson loops in great detail, and I wanted to do it where I can actually do explicit calculations quite easily. And I think it's different from the way you're used to thinking about Maxwell theory, so I think there is something interesting there. And then I moved to Yang-Mills theory and defined Wilson loops there and discussed other gauge invariant operators and discussed Hooft loops briefly and surface operators. Please do the exercises and we'll go over them in the tutorial.